This presentation, I will talk about convolutional neural networks. I decided to remove some information from this presentation that is related to training and some of the activation functions and place it into a separate presentation on training neural networks. So in this presentation, we will focus on the architecture of convolutional neural networks and how they work in general. So this presentation is heavily based on a blog entry by Karn called An Intuitive Explanation of Convolutional Neural Networks, and I linked it up over here. I also use some information from Wikipedia. So let's start out a little bit. So CNNs can be looked at as a more robust pattern matcher than simple feed-forward networks. The initial idea was developed in the late 80s, but so like the most successful, or the first successful CNN that made a splash was developed in the 90s and then published in the late 90s. So they are successfully used in image and video recognition, recommender systems, medical image analysis, as well as natural language processing. So that's kind of interesting. So why use convolutional neural networks rather than feed-forward networks? In the programming assignment on neural networks, you will actually use a feed-forward network to classify images. In particular, you will be recognizing the digits 0 to 9. However, the input to your feed-forward network is rather small, and there's always only one piece of information, i.e. the digit. The key problem, though, is that a feed-forward network can be foiled, if you wish, if we shift an image over by several pixels, because it's just like hard-coded to focus on the pixels that are presented to it. CNNs are what we call shift invariant. So even if the image is shifted over a little bit, a CNN will be able to successfully classify an image. The way CNNs do that is they will, in an iterative fashion, focus on increasingly larger patterns. And that's kind of like what we need to understand today. Here is a sample architecture of a CNN. So we have an image on the left, and then we have this pattern matcher that gets larger and larger, and eventually we have a classifier, which is a good old-fashioned feed-forward network. So let's understand this left side over here first. Well, let's focus on it for just a moment. So the pattern matcher consists of several iterations of two layers, a convolutional layer and a pooling layer. Okay, so which in this particular example we have one set and another set. The classifier consists of a fully connected feed-forward network, two layers over here, to produce the output. So what are some image recognition tasks that CNNs can do? So here's an example. It can recognize the car, and a person, and a horse, and a dog, and another person. In this image, a dog and a cat. And again, these are the probabilities, if you want to interpret this way, of a successful recognition. So that's pretty cool stuff. And again, even if the car were over here or over here, it would successfully recognize it as a car. So how does the image processing look like? So let's have a look at the data. And I switched the image around a little bit. And so here's a color data, a color image. And so a lot of times color images come in 3 colors. So hence we have 3 layers, if you wish, at the input. In this particular example, we have 224 by 224 pixels. And again, as you know, each color gets represented a lot of times by its shades. And so hence it's not just a single bit that we will be using over here. So that's what we start out with. In this particular example, you can tell that we somewhat process this thing so that we end up with 64 layers of data. This one here is called the convolutional layer. How that works, we'll see in a minute. It detects patterns in the data, and then the next layer, you can tell that the matrix gets smaller and also more numerous. So what we do over here is notice it's a quarter of the original size. Is we're sort of like zooming out, and so this is what I meant earlier when I said that we iteratively discover larger and larger patterns. This is called the pooling layer. So technically speaking, there's just one pooling layer over here, and then over here we have more convolutional layers. Here's a visualization of what we mean by this thing. So down here at the bottom layer, so this is part of, say, recognizing faces, we might pick up certain very, very low patterns, some lines if you wish. And on the next layer, we may pick out maybe eyes and noses and eyebrows and those sorts of things. And then over here, we might pick out entire faces. So that's kind of like the objective, or that's kind of like a way to visualize what these things are doing. So we focus on increasingly larger patterns, but each layer we sort of like discover some patterns. So how does that work? So let's dissect one of those things. This is a very, very, very simplified input image on the left. It's 5 by 5, and it's a black and white image if you wish. 1 is a black pixel, 0 is a white pixel. Again, very, very much simplified. So what we do in the convolutional layer, we apply a matrix to it. We call it a filter. So this is the filter over here. And again, the filters are typically much, much smaller than the original image. It's just that we have a small image to begin with. So over here we have a 3 by 3 filter. And what we do is we apply the filter to this matrix. So at first we're going to apply it over here to this portion. Not what I wanted. And then we multiply this one with this one, it gives us an output. Then we move over by 1 bit to the right and we apply it to this portion. And again, that gives us some output. And then we move over to this one here. And when we're done with this row, we move down a column. I'm sorry, when we're done with this row, yeah, we move down one row to over here. So that's what we do. So let's have a look at what that might produce as an output. So over here, if we multiply these things together, we have an output of 4. And we continue doing this thing until this entire feature map, as it is called, is filled up. So again, we do this row by row, 1 pixel at a time. You may notice that in our example, the feature map is 1 pixel smaller in each dimension. Again, you have to remember that the original image is quite large. So in the end of the day, it doesn't matter. We lose 1 pixel along the border. Most of the time, important information is not at the borders of images. It's sort of like towards the center, right? If you want to keep the original image the same size, what you could do is you could pad this image with zeros on the outside. And so then you have then the resulting image, the feature map, is the same size as the original image. So the number of pixels that we move over is called the stride. In our example, the stride is 1. If you were to increase the stride to 2 or 3, then the resulting feature map would be smaller. But in the examples that we have seen, the stride is 1. So what sort of filters might we be interested in applying? So as you can tell over here, we applied a lot of filters. So let's have a look at some of them. So here's an example of a filter. This is the original image. And this is, well, still the processed image, which is the original one again, because we use the identity filter. So if we apply this thing, again, you may go back to this one over here. Then we always pick out this image, this. All right, so we just focus on the bit that we're focusing on, and it'll produce the identity. So that makes sense. But there are other filters. So we might use a filter for edge detection. It's like a little bit hard to see. If you want to see the original, go to this Wikipedia link over here. So here's the matrix that we would use to multiply this original image to get to this. This one here to get to this. This one here to get to this. So here you can sort of like tell the outline a little bit better than over here. Here's some other ones. We can sharpen something, we can blur it, all sorts of filters that we might be interested in using. So the next thing then is the pooling. Again, we have discovered something, so we want to zoom out. So that's what we need to do next. So here is an example of what happens when we do pooling. Again, we have several options to do that. In this particular example, the stride is 2. And in essence, what we're doing, we're applying a 2x2 filter if you wish. So this one here, and if we do that, then we reduce the image to a quarter of its size. So this one over here will be reduced to this one over here, stride 2 will be reduced to this one to this one, this one to this one. In this particular example, we have a max filter. So we pick out the maximum in each of these little quadrants, 6, 8, 3, and 4. But there are others. We could produce the sum of all these elements. So here's how that looks like for an image. Down here we do the sum, over here we do the max. So reducing the image size. So then we keep on doing this thing. So we keep on using convolutional and pooling until we're finally at the fully connected layer. So what we have over here is then we have the classifier. Again, as we have seen before, a feed-forward network. What we do in CNNs is we use a softmax function here at the end. So you may notice that conveniently all of these values add to 1. And so the softmax value does that exactly. And so it's a form of normalizing things. And then if you want to have binary output, then you probably produce 0, 0, 1, 0. All right, that's it for this presentation. Please do have a look at the demo and my narration of the demo. And then I will have a separate presentation on training these networks. I'll see you then. Bye.